In section 7, we're going to apply the fundamental theorem of algebra and also find and classify solutions of polynomial functions. So in our key vocabulary here, we need to know what repeated solutions are. We're going to also look at irrational conjugates and complex conjugates. Now these are solutions you've already gotten before. You've found irrational conjugates and complex conjugates through the process of completing the square and using the quadratic formula, but we haven't necessarily called them by these names before, so we'll talk about these a little further on. Now, types of things that we would use to solve, use these skills to solve problems. We have here a problem where I've got a tachometer in a boat. So a tachometer measures the speed in RPMs, or revolutions per minute, at which an engine shaft is rotating. So it's really a measure of how hard is your engine working. If you drive a manual transmission vehicle, you normally would have a tachometer, and it would tell you how fast the engine is running, and that also tells you when to shift gears. So we're looking at a specific boat, and we have a model for the speed of the engine shaft in hundreds of RPMs and the speed of the boat in miles per hour. So the speed of the boat is s, and x is the speed of the engine shaft, and we can see then that depending on how fast the engine shaft is moving, then how fast is the boat moving in miles per hour. So what we want to know is, what is the tachometer reading? So what are the revolutions per minute of the engine shaft when the boat reaches 15 miles an hour? Before we solve this problem, we're going to go ahead and work on some other ideas, but we'll finish this up at the end of the lecture. So we're supposed to supply the fundamental theorem of algebra, and this is it. So the theorem says that if f of x is a polynomial of degree n, where n is greater than 0, so it's a polynomial with a degree that's greater than 0, so first degree, second degree, third degree, fourth degree, then the equation f of x is equal to 0. Remember, we set polynomial functions to be equal to 0 in order to find solutions. And it says it will have at least one solution in the set of complex numbers. So that's all that really means is, as long as you have a polynomial with a positive degree, you can find a solution. And the corollary says that for the same circumstances, a polynomial with a positive degree, then the equation f of x is equal to 0 has exactly n solutions. N, remember, is the degree, provided that each solution that is repeated twice is counted as two solutions. So we talk about repeated solutions. And what's helpful, we talked about this in quadratic functions. We remembered that when we used the discriminant, we could find out if our polynomial had two real solutions, one repeated solution, which would be two solutions, or two imaginary solutions. So you saw that in a second degree function, we found two solutions, and our solutions always sort of came in pairs. So, and a solution that's repeated 3 times gets counted as 3 solutions. So what they're saying is you count solutions even when they repeat. Then you know that the number of solutions that you have is equal to the degree of the polynomial. So that's all they're really saying here is if you have a degree n, then you have n solutions. Okay? That helps us in terms of knowing whether or not we're finished. So if I wanted to go through and find the number of solutions, or the number of zeros that we have in a problem, all I'm really going to look at is the degree. Fourth degree, third degree. The number of solutions matches the degree. So for right now, this is very simple. We're really just identifying the degree of the polynomial. Later, when we're solving our polynomials, it will be helpful so that we'll know, did we find all of the solutions? Okay, so just to practice this, go ahead and do problems 5 and 6 in the exercises for 2.7, and then come back to the lecture. So here we go through. We want to find the zeros of our polynomial function. So I've got a couple of fourth degree functions here. And going back to the skills we've learned before, I know that the total number of rational zeros would be the factors of the constant divided by the factors of the leading coefficient. So the leading coefficient is 1, and the factors of 8 are 1 and 8 and 2 and 4, and those are the factors. So I could test plus and minus 1, 2, 4, and 8. I would probably, with a fourth degree function, I would go right to synthetic division. I have 1, negative 6, 7, 6, negative 8. Fourth, third, second, first, and 0 power. I've accounted for them all. And now I might start testing. If I add down, I find 1 times 1 is 1, negative 6 plus 1 is negative 5, times 1 is negative 5, plus 7 is 2, times 1 is 2, plus 6 is 8, times 1 is 8, negative 8 plus 8 is 0, so 1 is a solution. Okay, so now I had a fourth degree equation here, fourth degree. This now here will be a third degree function. These are the coefficients of a function. It would be x cubed minus 5x squared plus 2x plus 8. And I can go ahead and do synthetic division with these. Now what's important is that if I'm going to find a repeated solution, for instance 1 might be a repeated solution, I won't find it by retesting in the original function. So each step down I have a smaller polynomial to work with, and it's a little faster for me to find my solutions. So I'm processing through doing synthetic division here, and I don't end up having a 0 for a remainder, so 1 was now not a solution. So again, it's good for me to keep track of what has failed. Right? 1 was a solution, but now 1 has failed. I'm not going to try it again, but I will try negative 1. Oh, fabulous. So negative 1 is also a solution. And now I have a second degree function. This is x squared minus 6x plus 8. And if I want to go ahead and solve this, I would want factors of 8 that add up to be 6. That's 2 and 4. I know that my signs are the same and they're both subtraction. And I put in my 2 and my 4. My solutions from these, right, would be 2 and 4. I had a fourth degree function. It has 4 solutions. I've found 1, 2, 3, 4 solutions, and I'm done. Now I told you early in the semester that I was going to give you a tool to help do synthetic division because these problems can get to be a little bit long. So let me go ahead and show you how that works. So I have this sheet, Excel sheet, and it's good for polynomial functions that are all the way up to the 6th degree. Okay, so it will go ahead and help you out with those. I've gone ahead and put my coefficients in, 1, negative 6, 7, 6, and negative 8. And now over here, if I just put in values of k, right, so possible zeros, if I put in a 1, you'll see we'll get the same solution. I got a 0, and it automatically brings the coefficients for the new polynomial down. So now I have my third degree function. And if I put negative 1 in here, I know that was a solution. It shows me that 0 was the remainder, so then it brings my coefficients down to be a second degree. Now this is normally where I would tell you to bring it out and solve it like a quadratic like I did. But I can keep testing for rational solutions. So if I put in the 4 here, you see I get a 0, and if I put in 2 here, I also got a 0. So I have 1, negative 1, 4, and 2. So that's kind of how this sheet works. So now I'm going to use it to go ahead and solve this polynomial function. I want to put in my coefficients. I normally start from the 0, so the constant is 30. Right? I have negative 29 with the first power. I have negative 7 with x to the second power. I have 5 with x to the third power, and I have 1 with x to the fourth power. And, you know, I went ahead and I left some numbers in, but you see, 1, I already know 1 is a solution. So that's nice. See, I got a 0 here. So that makes 1 one of my solutions. But I want to go back for just a second, and I want to figure out what are the possible solutions. Because for 30, right, I have plus and minus 1 and 30, 2 and 15, 3 and 10, 5 and 6. So these are all the numbers that I might want to test. I found one solution. That's great. Now I'm going to try to find another solution. So let's try 1 again and see. No, 1 doesn't work. Now I try -1. Now that doesn't work. I try 2. 2 is a solution. That's great. And now each time I find a solution, I move down a level. So now I have a quadratic function. Normally I would go ahead and pull that function out. So my coefficients are 1, 8, and 15. So I have 1x squared plus 8x plus 15, and I want to factor this. I know my signs are the same, and they're both positive. Factors of 15 that add up to be 8 would be 5 and 3. So my solutions would be -5 and -3, plus the ones I got from the Excel file, 1 and 2. One and 2. Those are my 4 solutions. Okay, so if the tool helps you, now let's be practical. I've given you a tool so you can do your homework a little faster, so this sheet can help you do that. It'll help you find zeros really quickly. You'll see if I put in -3 here, I'll get a 0, and if I put in -5 here, I'll get a 0. The sheet will only find rational solutions, right? So it won't find irrational numbers or imaginary numbers. That's why when you get to the point that you have a quadratic, you should pull it out and solve it in the ways we learned in Chapter 1. But if this tool will be there to help you, but remember you won't have it for things like tests or quizzes or things like that. So it's there to help you with your homework, but it doesn't replace understanding how to do synthetic division on your own. Okay, but go ahead and practice. If you want to download the file, you can get it off of the Moodle sheet. Practice by doing problems 12 and 13, and then come on back to the lecture. All right, so this is relatively, I think you've already experienced this. So these are theorems that help you to make sense of things you've already experienced in solving. And you'll notice that anytime you have solutions that are imaginary solutions or are solutions that have irrational values in them, right? We always have plus and minus. We always get plus and minus either from completing the square. When we take the square root of either side of the problem, we add in a plus or minus. Or when we do the quadratic formula, the plus and minus is already built in. So you've already experienced the fact that whenever you find an imaginary solution, they come in pairs. And the pairs are conjugates because the only thing that changes are the signs, plus and minus. And the same with irrational numbers, plus and minus. So what this is really telling you is that if you know one solution that is an imaginary solution, its conjugate is also a solution. And the same with irrational solutions. If you have an irrational solution, its conjugate is also a solution. And that's because sometimes you're going to know some of the solutions, but not all of the solutions. And it's important to keep track of the fact that these types of solutions, complex numbers and irrational solutions, always come in pairs. So we've gone through the process of solving polynomials by factoring them and finding solutions from the factors. And now what we're going to move into is the reverse of that, which is taking the solutions, putting them into factors, and then creating the equation. So I have a function that has solutions of -2, 1, and 3. I know that if I have these k values that are zeros, then x minus k is a factor. So I'm going to have x minus -2, that's x plus 2, and x minus 1 is a factor, and x minus 3 is a factor. And if I want to write this polynomial function, I just need to multiply these all together. So when I multiply these two together, I'll get x squared, and I'll get plus 2x minus 1x, that's plus x, and I have minus 2. And I'm going to multiply that times x minus 3. X times x squared is x cubed. X times x is x squared. X times minus 2 is minus 2x. And -3 times 2x is negative 3 times x squared is minus 3x squared. Negative 3 times x is minus 3x, and negative 3 times negative 2 is plus 6. And when I combine like terms, I'll have x squared and minus 3x squared, so that's going to be minus 2x squared. And I have minus 2x minus 3x, that's minus 5x plus 6. So this is the polynomial that has these solutions. Okay, and remembering the information I had on the previous slide, if 3i is a solution, then I know that minus 3i is a solution. And I know that if 2 minus I is a solution, then 2 plus I is also a solution. So that was sort of the point in getting that previous bit of information, that I know that my imaginary solutions or my irrational solutions come in pairs, so they give me one part of the pair. I have to put in the other part of the pair. So again, these are my k values, so my solutions, or my factors, would be x minus 3i, x minus negative 3i, so that's going to be plus 3i. And I'm going to have x minus 2 minus I, and I'm going to have x minus 2 plus I. Excuse me, let me move that over because that's just flat illegible. Sorry about that. So x minus 2 plus I. Right? When I simplify these by distributing the subtraction, I'm going to have x minus 2 plus I and x minus 2 minus I. Right? Let's keep these guys separate from each other. X minus 3i, x plus 3i. So now I want to multiply these out, so I'm going to multiply these two together and these two together. I want to always multiply the conjugates times each other right away, because they're going to simplify what I get. I don't want to multiply the x plus 3i times this trinomial. It's not going to simplify well. It's going to be a lot of extra work. When I multiply these two together, I'm going to get x squared minus 9i squared. I know that because that's the way conjugates multiply together. I'll get this squared minus that squared. Right? When I multiply these guys together, and actually let me go ahead and simplify this, because this is, remember, I squared is negative 1. So this is minus 9 times negative 1 minus negative 9. I'm going to get x squared plus 9. Okay, that's great. When I multiply this times this trinomial times that trinomial, it's going to be a big thing. So I'm going to put it down here. X times x is x squared. X times minus 2 is minus 2x. And x times minus I is minus xi. Negative 2 times x is minus 2x. Negative 2 times negative 2 is plus 4. And negative 2 times minus I is plus 2i. And then I times x is xi. I'm going to have to go down to another line here. I times minus 2 is minus 2i. And I times minus I is minus I squared. So now when I go ahead and I simplify this by combining like terms, I'm going to have the x squared. I have minus 2x, that's minus 4x. I have minus xi and plus xi, they cancel. I have plus 2i and minus 2i, they cancel. And I have plus 4 and minus I squared, so that's minus negative 1, that's plus 1. So this plus 4 plus 1, that becomes plus 5. So the value of multiplying the conjugates is you saw that all of my i's, all the imaginary parts, went away. And now I'm left with multiplying these two polynomials together. So x squared times x squared is x to the 4th. X squared times 9 is 9x squared. Minus 4x times x squared is minus 4x cubed. Minus 4x times 9 is minus 36x. 5 times x squared is 5x squared. And 5 times 9 is 45. When I combine like terms, I'll have x to the 4th. I have minus 4x cubed I have plus 9x squared and plus 5x squared. That's plus 14x squared. I have minus 36x and plus 45. So this was the polynomial that had these as solutions. Okay, you notice 1, 2, 3, 4 solutions. I get a fourth degree function. It's a lot of work sometimes doing these. I don't really have any shortcuts for you. My only advice is always multiply conjugates together when you have them. So go ahead and get a little practice doing this. Go do problems 22 and 24, and then come on back. Okay, so now we have another interesting piece of information to help us understand solutions, the numbers of solutions, and what types of real number solutions I can get. So René Descartes, he's the guy who gave us the Cartesian plane, or the XY grid that we graph in 2 dimensions on, and a number of other things. So what he has determined is that if we can figure out the number of positive real zeros, it's equal to the number of changes in the signs of the coefficients, or less than that by an even number, and then for negative real zeros is equal to the number of changes in sign for the coefficients of f of negative x, so that would make some changes, or it's less than this by a negative number, or sorry, an even number. So meaning I could back down by 2's. Right? So when we look at that in practice, if you take a look at a problem like this one, right, I have positive, and when I go to negative I have 1 change, and then here it doesn't change again. So I had 1 positive. Okay, and now if I plug in negative x for everything, so if I have negative x to the 4th minus negative x squared minus 6, then taking this to the 4th power will be x to the 4th. This will also, you see, it doesn't change, right? If I had some odd powers in, it would change the signs a little bit. So then I would also have 1 negative. Okay, so but what helps there is that if I know that if I have 1 positive solution and 1 negative solution, but I have 4 solutions, that means I have 2 imaginary. Now in this case, there weren't many options for how this could come out, so I was able to tell right away that I have 1 positive number solution, 1 positive real number solution, 1 negative real number solution, and 2 imaginary solutions. So if we do that again here, we have, there's 1 change, and there's a second change. So I have 2 or 0 positive. And if I go ahead and do f of negative x, you see now this time my signs will change a lot. So this will become negative x to the 5th. And this is going to be negative x cubed, but it's minus 2, negative 2. Minus negative 2 becomes plus 2x cubed. This is going to be squared and become positive. It's going to be minus x squared. This is going to be minus 6x plus 5. And now when we talk about my changes, I have 1 change, 2 changes, 3 changes. So this would be 3 or 1 negative out of my total 5. So you can see that I could have 2 positive and 3 negative, and that would be 5 solutions. I could have 2 positive and 1 negative. That means then I'd have 2 imaginary solutions. That would equal 5. So whatever equals 5. And there are a wide range of different possibilities. So what you want to just practice right now is checking the number of times the sign changes and the different method, the different possible solutions, right? I could have 0 positive, 3 negative, and then I'd have 2 imaginary. I could have 0 positive 1 negative, and 4 imaginary. So all of those different possibilities can come up from this in terms of speculating what types of solutions do we have. Now, in Descartes' time, he didn't have any technology to help him, so this helped a lot in terms of narrowing your focus in terms of what work you were doing. So to get a little practice with that, do these problems, 35 and 36. Come on back and we'll finish out the lecture. So here we have our problem about the tachometer. So the key element here is they want to know what is the tachometer when the boat reaches 15 miles an hour. So 15 is my speed. So 15 is going to be equal to 0.00547 x cubed minus 0.225x squared plus 3.62x minus 11. And to solve this, I want to set it to be equal to 0, so I'm going to have 0.00547x cubed minus 0.225x squared plus 3.62x. And then I subtracted 15, so negative 11 minus 15 is minus 26. So if I solve this polynomial, then I could go ahead and find my solutions. And this doesn't look like a lot of fun to me, right? So if I were sitting with a Texas Instruments calculator on my desk, and I'm not, I would probably plug these values into a calculator and then look at a table. And remember, I'm looking for the solution. I'm looking for the spot on the graph where y equaled 0. And that's always my x-intercepts. That's what I'm looking for. So now I didn't have a TI calculator, and you may not have a TI calculator when you're working at home, but I do have access to the internet, and I can go ahead and use this graphing calculator. So you see I've plugged this function in here, and I asked it to graph, and now I'm looking for my solutions. So here's my x-intercept. It's at 19.9. X is 19.9 when y is equal to 0. So that's my solution. X will be equal to 19.9. Now, there are other ways I could have gone about this, I suppose, but it seems you can see with a cubic function, boy, I could have tried to graph this, or I could have tried to graph it by hand. I could have tried to factor it. It would have been really difficult to do. I'm not going to find 19.9 in my list of rational zeros, maybe, but the factors of 26 divided by the factors of 0.00547, that's no fun. So this is a case where graphing was really a lot of help. And having a graphing tool really made all the difference in terms of being able to get this done.